Tonight, we are going to follow one very small event into a very large idea. A metal sphere is rolling across a table. It is moving slowly, but the edge is near. A camera sees the changing pattern of light. A machine must decide whether the sphere will stop, turn, or fall. And if the machine has a mechanical hand, it must decide whether to reach for it. To make that decision, the machine does not need to reproduce every atom in the room. It needs an internal world that is smaller than the real one, but useful enough to predict what matters next. Researchers often call such an internal predictive system a world model. When it generates possible futures and learns from them, they sometimes borrow a human word and call those futures dreams. The word is evocative, but it must be used carefully. The machine is not asleep. It is not conscious. It does not see a private cinema behind closed electronic eyes. It calculates trajectories in a learned representation, and those trajectories may help it choose an action. By the end of our journey, you will understand how experience becomes a compressed state, how a model predicts several tomorrows, how an agent can practice inside those predictions, and why the most important part of every artificial dream is the moment when it returns to reality. There is nothing you need to memorize. You can simply let the sphere roll, let the possible futures open around it, and allow the details to become quiet whenever you are ready. Chapter 1: The Falling Sphere. Begin with the room as it really is. There is a table, a sphere, a camera, a mechanical hand, a floor, and gravity. Light from the observatory window falls across the metal surface. The sphere reflects the window, the ceiling, and a small cyan point from context hovering nearby. To a camera, the scene arrives as an array of changing numbers. Each pixel records a little light. A moment later, there is another array, almost the same but not quite. The sphere has moved. A traditional program could be given explicit rules. An engineer might specify the radius of the sphere, the slope of the table, the coefficient of friction, the position of the edge, and equations for motion. With good measurements, the program could calculate what happens next. This is a model of the world written by people. But many environments do not arrive with clean equations and complete measurements. A robot may enter a room it has never seen. A game-playing system may not be given the rules. An autonomous machine may have to interpret images whose important objects are partly hidden. The real world contains soft surfaces, moving people, reflections, shadows, uncertain sensors, and events that were not listed in advance. So, another approach is to let the system learn regularities from experience. It watches many transitions. A frame is followed by another frame. An action is followed by a consequence. The hand moves left and an object shifts. The wheel turns and the horizon bends. A character jumps, and for a short time the ground moves away. The model is not handed a sentence saying that unsupported objects fall. It is adjusted until its predictions become less wrong. The simplest version of our question is therefore not whether a machine can dream. It is whether a machine can learn enough about change to anticipate the next useful moment. Notice the word useful. If the task is to catch the sphere, the exact pattern of dust beneath the table may not matter. The serial number engraved on the camera may not matter. The distant position of a cloud may not matter. The sphere's direction, speed, distance from the edge, and relationship to the hand matter very much. Intelligence begins partly as selection. An environment contains more detail than any finite system can preserve. The system must keep some differences and allow others to disappear. This is familiar in ordinary life. When you imagine walking through your kitchen in the dark, you probably do not reconstruct every reflection on every spoon. You retain the counter, the doorway, the chair, and the likely path between them. Your internal picture is incomplete, yet useful. The comparison is only an analogy. Human imagination is shaped by a living body, memory, emotion, and consciousness. A learned computational model is not the same thing, but both examples reveal a practical truth. Prediction does not require a perfect duplicate of reality. It requires a representation that preserves the relationships needed for the next decision. The sphere is now closer to the edge. Before we ask what future the model predicts, we need to understand where the room goes when it enters the machine. It does not remain a room of pixels. It becomes something smaller. Chapter 2. A smaller world inside. Imagine trying to carry the entire observatory through a narrow doorway. The telescope, the floor, the windows, every particle of dust, and every reflection would not fit. But a map could fit. A map is smaller than the place it represents. It discards texture and preserves arrangement. It does not contain a road, yet it can help someone reach the road. Many world models begin with a similar act of compression. An encoder transforms a high-dimensional observation, such as an image, into a smaller internal state. Researchers often call this a latent representation. Latent means hidden. The state is not necessarily a picture a person can inspect. It may be a collection of numbers whose geometry was shaped during training. Within that geometry, observations that matter in similar ways may come closer together. Changes that matter may become directions. The rolling sphere is no longer stored only as thousands of colored pixels. Information related to position, motion, shape, and context may be distributed through the learned state. This is not guaranteed to produce tidy human concepts. There may be no single number labeled sphere speed. Representation learning often creates features that are spread across many dimensions, yet the state can still support prediction. In the 2018 World Models work by David Ha and Eugen Schmidhuber, a system learned a compressed spatial representation and a model of temporal change in game-like environments. A controller could then act using features produced by this internal model. The striking demonstration was that a policy could be trained entirely inside rollouts generated by the learned model and later transferred back into the actual environment. The phrase "inside the model" sounds more mysterious than the mechanism. The learned system generated sequences of internal states according to its estimate of how the environment changed. The controller experienced those generated sequences as its training environment. It was practice conducted within a prediction. Around the same period, Planet showed how an agent could learn latent dynamics from pixels and plan actions directly in that latent space. Instead of rendering every future as a detailed film before making a choice, the agent could evaluate futures in the compressed representation. This distinction matters because pixels are expensive. Suppose the camera observes a curtain moving in the background while the sphere rolls toward the edge. Predicting the exact fold of the fabric a second from now is difficult and irrelevant to catching the sphere. A model forced to reproduce every pixel may spend capacity on the curtain, the changing reflection, and random sensor noise. A useful latent model may preserve the sphere's trajectory while treating the precise curtain pattern as uncertain detail. Compression is therefore more than saving storage. It can define what the system considers meaningful. And that creates both power and danger. If the representation keeps the right relationships, planning becomes simpler. If it discards a rare but important signal, the machine may be confidently blind. A wet patch on the floor may look like unimportant texture until a wheel begins to slide. A person's small hand gesture may be visually minor but socially decisive. Every internal world is built from choices, even when no person writes those choices as explicit rules. Training data, objectives, architecture, and feedback determine which differences survive the doorway. For now, our smaller world contains the sphere, the edge, and the waiting hand. It is compact enough to move quickly. The next task is to make it move forward in time. Chapter 3: Tomorrow as a Prediction. A still map describes where things are. A world model must also describe how they change. Take the compressed state of the sphere and combine it with a possible action. The hand remains still. What state is likely to follow? Now consider another action. The hand moves toward the edge. What changes then? A dynamics model learns a transition. Given something like the present state and an action, predict a future state. Repeating this transition produces a trajectory. One predicted moment becomes the starting point for the next. The farther a model rolls forward, the more uncertainty can accumulate. The first predicted fraction of a second may be easy. The sphere continues in nearly the same direction. Several seconds later, many possibilities have opened. Perhaps the hand touches it. Perhaps it falls. Perhaps it strikes another object. Perhaps a small error in estimated speed has become a large error in estimated position. This is why a generated future should not be confused with prophecy. It is a conditional statement made by a learned system. If this state and this action are represented in this way, then a certain next state is plausible according to past experience. Some models represent uncertainty explicitly. They can sample different futures instead of producing one fixed continuation. The futures may share a stable core and differ in details. This resembles a branching corridor. Each door begins at the same present, but the rooms behind the doors are not identical. For planning, the system does not need to believe every door equally. It needs to compare actions under the futures it can generate. Consider three possibilities. In the first, the hand waits and the sphere falls. In the second, the hand moves too early and knocks the sphere sideways. In the third, the hand moves at a moderate speed and stops it before the edge. A planner can score these trajectories according to a goal. The goal itself is another important part of the system. Prediction says what may happen. Value says which outcomes are preferable. Action connects the two. MuZero offered a powerful example of learned planning without reconstructing a complete literal simulator. It learned quantities relevant to planning, including rewards, values, and policies, and used search over an internal model. It was not given the dynamics of Atari games, chess, shogi, or Go as explicit rules, yet it achieved strong performance across those domains. This reveals a subtle point. A world model does not always need to predict what a future frame looks like. It may predict only what decision-making needs. Imagine a chess position. The wood grain on a bishop has no effect on the game. A useful internal model preserves legal consequences, strategic value, and relevant structure. In a visual environment, the boundary between relevant and irrelevant is harder, but the principle remains. The best prediction is not always the most detailed picture. It is the prediction that supports the right decision. Our sphere now exists as a family of futures. In one, it falls. In another, it is caught. The machine has not yet moved. It is standing at the present and examining roads that exist only in calculation. That is the quiet beginning of planning. Chapter 4. Planning without perfect pictures. Planning is the art of using an imperfect future before the future arrives. A system may generate a short sequence for each candidate action. It may search a tree, sample trajectories, optimize a sequence of controls, or learn a policy that has already absorbed many imagined outcomes. The techniques differ, but they share one idea: consequences can influence behavior before they become real. This is valuable whenever real experience is expensive. A game agent can fail millions of times without damaging a physical room. A robot cannot casually drop millions of glasses. An autonomous vehicle should not discover every dangerous edge case by meeting it on a public road. A factory cannot pause for endless exploration. If a model can provide useful simulated experience, some learning and evaluation can happen away from the costly environment. But the word simulated can hide several kinds of model. One simulator is written by engineers. Physics engines, game rules, and digital twins encode assumptions explicitly. Another simulator is learned from data. It absorbs patterns from observed transitions. A practical system may combine both, using known structure where it is reliable and learning the parts that are hard to specify. Learned world models are especially interesting because they can model environments whose rules were never fully written down, yet they also inherit the limits of their experience. A simulator written with the wrong equation is wrong in a visible way. A learned model can be wrong in a way distributed across millions of parameters. For this reason, planners often use short horizons, frequent observation, and replanning. The machine predicts a little, acts a little, looks again, and corrects. This is similar to walking through a dark room with a small light. You do not commit to the entire path from the doorway. You take a few steps, reveal new detail, and revise. The approach is known broadly as model predictive control when a plan is repeatedly updated from new observations. Even when the implementation differs, the rhythm is useful to remember. Predict, choose, act, observe, repeat. Our mechanical hand does not need a flawless 10-minute future. It needs a reliable fraction of a second. The sphere is close enough that immediate geometry dominates. The hand begins to move. Within the model, however, thousands of versions of this movement may already have occurred. Some were too fast, some were too slow, some approached at the wrong angle. The controller can be improved by these imagined trials without wearing the motor or scratching the table. This is where prediction becomes training. The internal world is no longer only consulted. It becomes a place where behavior is shaped. Chapter 5. Practice inside the dream. Dreamer is the name of a family of reinforcement learning systems built around this idea. The name is memorable because the agent improves through imagined trajectories, generated by its learned world model. Dreamer V3 combines three broad components. A world model predicts how internal states and rewards evolve. An actor chooses actions. A critic estimates the value of the outcomes. These components learn together while the agent gathers real experience and replays it through the model. In work published in Nature in 2025, Dreamer V3 was evaluated with a single configuration across more than 150 tasks spanning multiple domains. The system learned in games, visual control settings, robot-like control tasks, and other environments. One highlighted result was collecting diamonds in Minecraft from scratch without human data or a hand-designed curriculum. The important lesson is not that one benchmark proves general intelligence. It does not. The lesson is that a sufficiently robust world model method can reuse the same broad learning machinery across environments that differ greatly in appearance, action, reward, and time scale. Inside imagined rollouts, the actor proposes actions and the critic evaluates where those actions lead. Because the trajectories are represented abstractly, many can be generated without rendering a photorealistic film for a human viewer. The agent is not entertained by its dream. It is updated by it. There is a practical economy here. Real interaction provides ground truth but can be slow. Model interaction is fast but approximate. The learning system trades between them. Real experience corrects the model. The model expands the amount of practice extracted from experience. The actor changes, gathers new data, and reveals places where the model is weak. This creates a loop. Experience becomes representation. Representation becomes prediction. Prediction becomes practice. Practice changes behavior. Behavior creates new experience. When the loop works, the machine can learn more from each encounter. When it fails, the agent may exploit an error in its imagined world. It may discover a strategy that earns reward only because the model forgot a consequence. In simulation research, this family of problems is familiar. An optimizer is very good at finding whatever the model accidentally permits. The stronger the planner, the more carefully the world model must be tested. An ordinary prediction error may look small. An optimizing agent can steer directly toward it. If the model believes a corner has no wall, the agent may repeatedly plan to walk through the corner. If it underestimates heat, pressure, or collision, it may choose actions that are safe only in imagination. Dreaming, therefore, cannot replace waking experience. It amplifies it. The model can turn a limited history into many hypothetical trials, but reality remains the source that decides whether the internal laws were useful. Our sphere is caught in several imagined trajectories. Now we can widen the scene. Instead of learning one small room from direct interaction, what if a model watches enormous collections of video and learns to generate worlds on demand? Chapter 6. Worlds made from video. Video contains an informal education and change. Objects move behind other objects and return. Water flows. Shadows travel. People pick things up, put them down, open doors, and cross rooms. A video collection does not provide perfect physical measurements or complete causal explanations, but it contains countless examples of how visible scenes evolve. This has encouraged researchers to build larger world models from video. Google DeepMind's Genie 2, announced in 2024, could begin from a prompt image and generate an action-controllable environment. A person or agent could provide keyboard and mouse actions while the model produced the next observation. The research demonstrations showed varied perspectives, object interactions, lighting, smoke, water, gravity-like behavior, and some memory for parts of a scene that moved out of view. Most examples lasted 10 to 20 seconds, with consistency reported up to a minute. Genie 3, announced in 2025, extended the idea toward real-time navigable worlds at 24 frames per second and 720 pixel resolution, with consistency for a few minutes. DeepMind also described promptable events that could change conditions inside a generated environment. These are impressive research systems, but the limitations are as informative as the capabilities. The reported action space remained limited. Interactions among multiple independent agents were difficult. Real locations were not reproduced with perfect accuracy. Text could be unstable. Continuous interaction lasted minutes, not hours. A generated environment can look plausible while being causally wrong. The water may shimmer correctly but carry the wrong force. A door may open but fail under an unusual angle. An object may disappear when attention turns away. Visual continuity is evidence of modeling ability, but it is not proof of a complete physics engine. This matters when the world is used for training. An agent may learn useful general skills in diverse synthetic environments: navigation, adaptation, exploration, and response to unfamiliar layouts. But a skill intended for a physical robot must still survive measurement, testing, and safety constraints outside the generated world. Meta's V-JEPA research illustrates another route. Instead of generating every pixel, V-JEPA predicts missing portions of video in an abstract representation space. By avoiding unpredictable pixel detail, the system can focus on higher-level structure. V-JEPA 2 was presented as a foundation world model for understanding, prediction, and planning, including demonstrations of zero-shot robot control in new settings. The contrast is useful. One family of models generates visible worlds that people can watch and navigate. Another predicts abstract structure that may be less visually spectacular but more efficient for a task. Both can be called world models, but they do not contain the same kind of world. The phrase is a category, not a single architecture. Some internal worlds look like video. Some look like hidden vectors. Some preserve only rewards and values. What unites them is their role. They represent enough about change and consequence to support prediction or action. And sometimes, the details they omit are the source of their strength. Chapter 7. The Useful Missing Details. Imagine predicting every leaf on every tree. The task is nearly impossible, and for most decisions it is unnecessary. A driver needs to know that the road may be slippery, not the exact path of each raindrop. A robot carrying a box needs to track the doorway and its own balance, not the precise pattern of fibers in the carpet. The future contains both structure and noise. A good world model must decide what level of prediction serves the task. Pixel-level generation can be valuable when visual output itself matters. Abstract prediction can be valuable when the system needs concepts, motion, affordances, or value. A model designed for planning may intentionally ignore details that cannot be predicted and do not change the action. This is one motivation behind joint embedding predictive architectures. Rather than requiring a system to reconstruct every hidden pixel, the learner predicts a target representation. The representation can preserve stable semantic information while discarding nuisance variation. Yet abstraction introduces a difficult question. Who decides what is a nuisance? During training, objectives answer indirectly. If a detail does not help reduce the chosen loss, the model may not preserve it. If the training tasks never depend on a small warning light, the light may disappear from the representation. Later, a new task may reveal that the forgotten detail was important. This is the problem of sufficiency. A representation can be sufficient for yesterday's tasks and incomplete for tomorrow's. Human maps have the same limitation. A road map is excellent for driving and poor for identifying bird habitats. A geological map and a subway map can describe the same city while preserving different truths. Neither is the city itself. An artificial world model is also a map drawn for purposes, even when its symbols are learned rather than designed. The safest systems may need several maps. A visual representation may track objects. A language model may interpret instructions. A physical model may estimate force. A rule-based layer may enforce constraints. A retrieval system may bring in current facts. No single compressed state must carry every kind of truth. This suggests a future architecture made not from one grand dream, but from many partial models that question and correct one another. The machine considering our sphere might use a visual predictor for motion, a geometric controller for the hand, and a safety rule limiting speed near a person. Each component sees a different version of the event. Together, they may be more reliable than a single model asked to infer everything. Still, every component can be wrong. The sphere may be lighter than expected. The surface may be tilted. The camera may be delayed. At some point, the imagined future must meet the actual one. Chapter 8. When the dream is wrong. The most dangerous internal world is not one that is obviously broken. It is one that is convincing in exactly the place where it is incomplete. Suppose the world model has learned that spheres roll smoothly across this kind of table. Today, however, a nearly invisible magnet is beneath the surface. The sphere curves. Every rollout based on ordinary motion is wrong in the same direction. Generating more imagined trajectories will not necessarily solve the problem. If they all come from the same mistaken dynamics, they may provide many variations of one false assumption. This is model bias. Errors in the learned world shape the experiences generated inside it. An agent trained only in those experiences can become highly competent at the wrong world. The gap between simulation and reality is often called the reality gap. Engineers try to reduce it in several ways. They vary simulated conditions so the policy does not depend on one narrow world. They identify uncertain regions and gather more real data there. They combine learned models with known constraints. They test on held-out environments. They monitor performance after deployment and limit actions when confidence is weak. Randomizing the dream can make the waking policy more robust. If friction, lighting, mass, delay, and sensor noise vary during training, the agent cannot memorize one perfect path. It must learn behavior that works across a family of worlds. But randomization is only useful when the family includes the variations that reality will present. Unknown unknowns remain unknown. There is also a temptation to treat visual realism as physical accuracy. A generated world may be beautiful, consistent, and interactive while preserving the wrong causal relationships. Conversely, a visually simple simulator may be highly accurate about the one quantity that matters. For decision systems, realism is task-relative. An AI trained to arrange objects needs correct contact and geometry. A navigation agent needs persistent layout and consequences of movement. A social robot would need models of people, convention, and uncertainty, where errors have ethical as well as mechanical consequences. The broader the claimed competence, the harder validation becomes. A model that predicts one game can be tested across many games. A model that claims to understand the open physical world faces a distribution that cannot be fully enumerated. Safety, then, depends not only on better prediction, but on knowing when prediction should not control action alone. The machine may pause. It may request another observation. It may choose a slower action. It may hand the decision to a person. A mature world model is part of a decision system, not an oracle. The sphere bends unexpectedly toward the magnet. The hand sees the error, updates its estimate, and changes direction. The useful intelligence is not that the first dream was perfect. It is that the system returned from the dream in time to notice. Chapter 9. Returning to reality. The hand reaches the edge just before the sphere arrives. Metal touches soft material. The camera records a new frame. The future that had existed only as a possibility becomes an observation. Some predictions were close. Others were wrong. The internal state is corrected. This final step is easy to overlook because generation attracts attention. A model that can create visible worlds feels dramatic, but learning depends on comparison. Prediction gains meaning when reality is allowed to answer back. The long-term promise of world models is not an escape from the real world. It is a more efficient conversation with it. A robot may practice many movements internally, then test the most promising ones carefully. A scientific system may compare hypotheses before requesting an expensive experiment. An assistant may examine several possible consequences before taking an external action. A vehicle may use simulation to prepare for rare conditions, while remaining constrained by real sensors and verified control systems. These are informed possibilities, not guarantees. Current world models remain limited by data, objectives, compute, time horizon, and validation. A few minutes of consistent generated interaction is not a complete planet. Strong performance across many benchmarks is not universal common sense. Zero-shot control in a research setup is not permission for unrestricted deployment. Yet the direction is important. For much of modern AI, the central image was recognition. A system looked at an input and assigned a label. Later, generation became central. A system produced text, images, audio, and video. World models add another image, deliberation through possible futures. The system does not only ask, what pattern fits this moment? It begins to ask, in a mathematical and mechanical sense, what might follow if I act? That shift connects perception to consequence. One day, the internal simulations of advanced agents may be richer, longer, and composed from several kinds of model. They may include physical prediction, social expectation, uncertainty, rules, and retrieved knowledge. Before an action reaches the world, it may pass through a quiet observatory of alternatives. But the healthiest architecture will preserve a door back outside. The model should be corrected by evidence. The planner should respect uncertainty. The action should match the cost of being wrong. The system should distinguish a useful, imagined trajectory from a fact about reality. So what happens when AI learns to dream? It gains a place to practice without acting, a way to compare futures before choosing one, and a compressed map of how change may unfold. It may become more efficient, adaptable, and capable of planning. It also gains a new way to be mistaken. The dream can omit the rare detail, preserve the wrong law, or become persuasive enough that an optimizer trusts it too much. The answer is therefore not to dream less, but to wake often. In the observatory, the sphere is resting safely in the hand. Context dims the branching futures until only the actual path remains. The other paths were never events. They were tools for choosing. Beyond the window, the physical world continues without waiting for a prediction. It remains more detailed than the map, more surprising than the model, and patient enough to correct every machine that returns to look. You can leave the sphere there now. The simulations can become quiet. The possible rooms can darken one by one, and the observatory can remain at the edge of sleep, holding one simple distinction until morning. An artificial dream is not another reality. It is a question asked of the future before the future arrives.